Good morning. What we are going to do today is continue on with Chapter 12, talking about concepts related to gradient boosting. Specifically, we're going to pick up where we left off last time and discuss the mathematical idea of gradient descent, which sort of underpins the entire technique. And then towards the end, I'll also do a review for quiz number 3, which is on Friday. Quiz 3 will cover Chapter 11 on random forests, and then the first bit of Chapter 12, basically where we're going to get up to through the end of today. On Thursday, rather than continuing on with Chapter 12, we're going to take a little break. This is partly just due to kind of the way the schedule changed around a bit and so on, and where Quiz 3 breaks. So instead, on Thursday, what I'll do is I'll talk about the final project, and if you're not kind of thinking about that yet, that's not a problem. That'll all, of course, be recorded and posted under the final project section. So if you're not here on Thursday and you plan to watch that later, that's not a problem at all. That's what I expect most people to do. It just happens to be a good time on the schedule to take care of it. So if you do want to get maybe an early start on the reading week and the break, feel free to do so, and then watch the video later. But I will be here to talk about the project for a little bit. It probably won't take too long unless there's a bunch of questions. So that's the plan for Thursday. All right, so now let's start what I mentioned, which is discussing gradient descent. This idea will play a crucial role both not just in Chapter 12, but also in Chapter 13 when we discuss neural networks. So it comes back again. So what this is an optimization process. The idea here is it's a way that we can mathematically improve. Built around the mathematical concept of the gradient. All right, now, multivariable calculus is not a prerequisite for this course. So if you don't know what a gradient is and you're not familiar with these ideas, that's not a problem. I'm going to discuss them somewhat informally and explain how this plays a role in this process. But we're not going to actually say you need to compute any of these by hand or anything like that, or actually have a formal definition. So let's talk about what a gradient is. So a gradient is a vector of derivatives. Given some function, such as for us a loss function, that depends on many variables, in our cases the different features, we can think about taking a derivative corresponding to each of those. Okay. So the idea is there is a vector of derivatives with one component in the direction of each independent variable. So however many independent variable we have, in other words, how many features are in our data set, the gradient is a vector in that dimensional space. So it could be very high dimensional. And the idea is you have one derivative in the direction of each of those. So the way to think about the gradient, especially in the context of what we're doing, is the gradient describes the local rate of change for each feature. So what do I mean by that? Okay. So at some point in the feature space, so think of the features if we take them all, form some multidimensional space, the feature space. And a point in there simply means a set of coordinates for each feature, right? One for each feature. So if we're somewhere in the feature space, which of course could be fairly high dimensional, what happens if we move away from that point by a small amount? So we make a small perturbation at that point in the feature space. We move away from it in any kind of direction we want. Okay. So moving away from that point, by a small amount, changes, well, it's going to change the feature values. Right? It moves to another point in the feature space, so each feature now has a different value. Okay. So the gradient, what it tells us is how much by how much. So, and it can do this for every direction. So any way that we want to move from that point, off the point, to some other point in the feature space, the gradient will describe how all the different features change. And as I've already alluded to, so with respect to gradient boosting in particular, we are interested in the changes in some loss function. So the rough idea here is our loss function is a function which depends on the feature values, right? Because the idea is how are we measuring the change in the target? Well, it's going to depend on the features. And so what we want to understand is, as we kind of move around the feature space, how is this affecting the loss function? In particular, right, most of our optimization problems are involving, say, minimizing a loss function. Okay. Although there are some examples where we're trying to maximize reduction and so on. So similar idea. Okay. So what the gradient is going to allow us to do is understand how these changes are taking place on some small scale. All right. Well, let's start with a very kind of simple type of picture, but nonetheless one that allows us to kind of illustrate reasonably well what's going on. Okay. So we're going to just pretend, to make things simple, that we're in two-dimensional space. Okay. Yeah. Okay. So we're just going to simply represent, on the horizontal axis, we'll have the features at the feature x, and on the vertical axis, we'll have the response or the target y. Okay. Now, as mentioned, the feature values, the feature here, I'm drawing it like there's just a single one, but you can actually think about x as just representing all the features, and it doesn't really ruin the idea. Okay. And now I'm going to draw a relatively simple idea for our loss function. We're going to say that as the features vary, the loss function looks something like this. Okay. Now, there is a point here and some corresponding feature value x, and at that point, we notice that it's flat, right? The rate of change is flat. The derivative is 0. And we can represent this geometrically by drawing a tangent line there. Okay. And what we see visually is at that point where we have slope 0, this is what we call a global minimum for the loss function. It has a minimal value, response value y. Okay, so that's a very simple looking setup. But one of the main points here is that this idea generalizes. Okay, so let's see what it maybe would look like if we go up to 3 dimensions, just so that we can kind of see that we're not working in even though we're going to draw these 2-dimensional pictures that are relatively simple, but the same idea actually does hold going forward. Okay, so we'll draw kind of a typical here. Yeah. So in 3-dimensional space, we often draw the axes this way. All right, and so let's say that this is feature x1, this is feature x2, and then the vertical direction will be the response y. Okay, so now we're saying we've got 2 different features, and y depends on both of them. And so now the graph of our loss function geometrically is going to be some sort of surface in 3-dimensional space. And it's hard to fully visualize this, but this is the idea. And then let's say that this point down here in the feature space, this is a global, we'll say that here's our global minimum. Now what we observe is that what we can look at now is not just a single slope, but we can look at the slope in the direction of each feature. So the idea is that the slope is going to be 0 in the direction of x1, and it's going to be 0 in the direction of x2. Oops, let me try redoing that one. Okay. So in other words, the rate of change in the direction of each feature is 0.
Julian, is it necessary that both of them have to be 0?
Okay, well, mathematically, yes. I mean, if you have a global minimum that occurs, that's also a local minimum. Okay, so in other words, if I've got a smooth surface like this, like the way I've drawn it, this is what's going to happen. The same thing up here. Now, if you don't require smoothness, if your function can say have discontinuities, then things can be different. You could have you could have your global minimum happen at like some weird point, like on the boundary and so on. And the slope, then you might not even have a slope. But basically, mathematically, yes. Like if I have a surface like this and the global minimum occurs somewhere on the interior of the surface, this is what's going to happen. Now, practically, when we use these techniques in real life, are we going to exactly achieve the slope being 0? No. And we'll see why. Okay. So this is just sort of like describing what the theory is. The idea is that at these points, whether in 2-dimensional space or 3-dimensional space or even higher, a point, what we call a critical point, is where the gradient is 0. So in other words, all the different slopes are 0. And if we go higher than this, we lose the ability to think about it geometrically, but the theory still works. Okay. But when it comes to actually, say, training an algorithm, a gradient descent algorithm, no, we're not going to actually get the slopes to be 0, because we're not going to be able to to do this well over kind of some smooth space. We have to limit, I mean, how much we can do, and we'll see why for various reasons. So this is all what we're talking about here is the theory, but we'll see a little later that the way we actually tend to implement this, it won't be the case that we'll necessarily find the global minimum, or there may be more than one, or and so on. So it's not in real life situations. It's not as clear what to do. All right, so minimizing or maximizing, if that's what we want to do, a smooth function involves determining where the gradient of that function is 0. Now, so another way to say this, maybe I should have said this earlier. What we're really looking at here is the multi-dimensional version of what's done in, say, just single variable calculus, where extrema occur at critical points. So, and a critical point is simply a point where the derivative, the first derivative, is 0. Okay, but now the idea is we have lots of derivatives in the directions of the different variables. We want them all to be 0. So it's taking that idea of a critical point for a single variable function and bringing it up into higher dimensions. Okay. So in the context of gradient boosting, so gradient boosting machines apply this idea to loss functions. Okay. So here's an example. So the boosting algorithm for regression trees, which we discussed at the end of last class. So that we discussed last time. Okay. Oh, what happened there? Oh, I accidentally minimized it. Yeah. Now, how does it work in this context? So, well, in the case of boosting regression trees, we're looking at sum of squares error, right? So for sum of squares error, the gradient, the values of the gradient correspond to all the residual errors. So minimizing the gradient, in other words, is essentially then the question of minimizing the residuals, right? So sequentially fitting, as we saw, the way we did, regression trees to the residuals of the previous trees iteratively lowers the total sum of squares error. Because as you do this, the residual errors get smaller iteratively. Okay. And so in other words, the gradient is getting smaller. We're getting closer to 0. Now here's a case where the actual practicality of it is going to break with the theory. We're not going to get our residual errors to go to 0. So we're not going to get the gradient being 0 by doing this iteratively, because we've got to stop at some point. It may be the case that if you looked at it like theoretically and you took a limit as you, like, say the number of iterations went to infinity, that the errors would reduce to 0, but we can't do that, right? We're not going to run, we can't run an infinite number of tree iterations for obvious reasons. So we're limited by the sort of practical context of what it is we're doing. Okay. But the idea here is that the gradient is going to decrease, hopefully, at essentially each step because of the iterative process. And that idea actually applies more generally. And so this leads to what we call gradient descent algorithms. So what we just described kind of motivates this by giving an example of one. So here's how, in some sense, the gradient descent process is implemented in some sort of machine learning algorithm. Okay. So the idea is we want to iteratively adjust parameters to optimize some function. So in our context, we usually think of this as a loss function. You could call it a cost function if you want, depending on the context, etc. And so the idea is that you're going to adjust your parameters and move around in the space. How does this happen? So at each step, the gradient descent algorithm what does it do? It calculates the gradient of our function for a given set of parameter values. And so the idea is the gradient is going to tell you kind of directions, right? It's giving you values of rate of change, which essentially are directional coordinates. Essentially, we're directions in the space, in a vector space. And what we're looking for is what we want to do is we want to go down as much as possible. So then moves in the direction of the steepest descent. One way that sometimes this is described is, imagine we're skiing down a ski hill and we're trying to get to the bottom as quickly as possible. And we're very good skiers, so we can kind of ski anything we want. Well, one way you might do this is try to take the steepest path down, right? And so you start skiing down a little bit, and then you'd kind of maybe adjust. You'd look and say, okay, now there's a steeper way to go. And you would sort of do that iteratively. Yeah, that's essentially what the algorithm is doing, right? The algorithm is skiing down as fast as it can. Question was, can the algorithm get stuck in local minima? Yeah, in fact, we'll talk about that a little bit later. You run into, if the loss, the pictures I drew earlier were very simple, right? And you might not expect the loss function to have that simple of a structure. What if the structure is more complicated? And then could you get stuck? And the answer is yes. And so then we actually introduce a way to deal with that. So that's coming up. Good question. We'll get there in a little bit. First, we want to talk about, just in general, how quickly do these algorithms work? And this leads to a hyperparameter, an important one, which is called learning rate. Okay. So this is a hyperparameter. In all gradient descent algorithms, not just for gradient boosting, but anytime this optimization process is used. And what it does is it controls the size of the iterative steps. Okay, so in other words, how quickly the algorithm learns. Hence the name learning rate. Okay, let me pull that up. So the idea then, and again, this picture is going to be pretty simple, but what's the kind of the idea behind gradient descent philosophically is something like this picture. So we start somewhere in the feature space on our, and then that has a value on the loss function. Now there's no good, because there's no reason we should be able to guess where the minimum is, right? At the start, you wouldn't expect that. So we start somewhere on the loss function, and then we have a learning step, which is essentially the loss function looking at the gradient and saying, okay, well, let's move down in the direction of steepest descent. So in the skiing example, right, the idea was how much time would you have between making turns, right, changing your trajectory to go in the steeper direction. That's essentially what the learning step is. It's a sort of like the amount of time in some sense, but not, there doesn't have to be time in the algorithm. Just how far do you travel along the loss function before you do another check, right? And you look for a different direction. That's what we're talking about. Okay. So the idea is that you would proceed iteratively with these down through the loss function. Hopeful, and I mean, this is of course a very simple picture. Here we're getting an improvement every time, and eventually we do reach a minimum. And that's partly just because of the simplicity of the diagram, but this is theoretically what we would like to happen in an ideal situation. Okay. So the learning rate is essentially going to control how big those jumps are from one point to the next. And you notice here, they're not all evenly spaced out. But that, of course, also has to do with the structure of the loss function itself. Okay. Okay. There's another name for this, which is often used as the hyperparameter name in algorithms such as in R. Learning rate is also called shrinkage. And so this name is commonly used as the hyperparameter in implementation packages. So in implementations in R and elsewhere. So for gradient descent algorithms. Okay. So it's a hyperparameter. So it can be controlled, right? It can be tuned, and size can be changed. Tuning gradient boosting hyperparameters is something we're going to discuss in 2 weeks. So the first lecture after the break. So we won't say too much about specific values of it right now, but let's point out and see kind of with the diagram what happens if it's sort of too small or too big. Okay. So if it's too small in some appropriate sense, then it takes a lot of iterations to reach a minimum. So, and then what's the problem with that? Well, of course, that's computationally inefficient. So you're gonna use a lot of runtime for the gradient descent steps, and this is getting back to Drew's question that we're going to handle here in a little bit, might get stuck. And we'll see what we mean by get stuck and what are some ways to deal with that. Okay. If it's too big, on the other hand, so if the steps are too big, the algorithm could jump over in some appropriate sense a minimum. So go too far compared to where it is, and then take many extra iterations to converge back to it. In particular, depending on the step sizes, it's possible you could sort of bounce like back and forth over the minimum. Okay, so that's so here's the end. Here's what that would look like. Okay, so two possibilities. On the left, we have too big, right? Make big jumps, and then we pass the minimum. And then if you think about it, we didn't draw further. Okay, so now at this point, you're not going to go back up the curve, right? You are going to descend, but then you might jump back again to near where you were before. And you might kind of ping pong back and forth until eventually it does reach the minimum. But that could take a lot of extra steps. And on the other hand, on the right, we see clearly the problem with too small is it's creeping along towards the minimum, and it's going to take a long time to get there. In that case, we're not going to jump over it, but we're going to take a lot of steps to reach the minimum. So these are sort of situations you want to avoid, and the way you avoid them is by treating it as a hyperparameter and tuning it appropriately. So that will come up in a couple weeks. Now, when does gradient descent work well and when does it not? So gradient descent performs best with convex loss functions. And generally speaking, what convexity means is that if you apply the function to the sum of features, that is going to be greater than if you apply the function to the features individually and then add the target values together. Okay, and so then geometrically, these are the sort of kinds of shapes we've been drawing. So something like a parabolic shape in 2 dimensions is a convex loss function, or the 3-dimensional version, some kind of paraboloid type shape like this, so some kind of like a bowl type shape. Okay. So then the natural question is, what about more general ones that don't have this convex property or something close to it? Okay. And so this is where we run into the problem of if we've got some complicated loss structure, we shouldn't expect a typical loss function to behave this nicely. Perhaps some of them do, but in general, there's no reason to think that they're all going to be convex. In particular, they can have lots of structure to them. And in some sense, if we think about the graph, to the extent it exists, or even in higher dimensions, there could be lots of sort of local features. Okay. So in that case, we have to introduce a technique that disrupts that structure. And this leads to the idea of stochastic gradient descent. So the idea here is we want to, so how do we disrupt kind of structures? Well, the typical way we do that is to introduce randomness. And this is the same thing we did with random forest, right? We disrupted structure in the sort of relationship between the data and the features on the splitting by introducing randomness, right? And that allowed us to kind of disrupt kind of relationships between where some of the features were more strongly influencing the splits than others. Okay. So we want to disrupt complicated structure in the loss function that would prevent us, that might prevent a gradient descent algorithm from reaching a global minimum. Okay, so what are the kinds of problems we can encounter mathematically? Many local extrema, what are called saddle points, where we have kind of fast directional decrease in one direction, we increase in another. What we might call plateaus, basically just regions in the loss function where the derivative is very small but not zero, so there's not much change happening, etc. Okay. So we want to do this. We accomplish this by introducing randomness. Okay. How? What we do, the usual way to do this, is sample without replacement a fraction of the training data at each iterative step. So every time we have an iteration in the algorithm, every time we make a step, we sample some of the training data, but not all of it. And apply the gradient descent algorithm only on that sample. All right, and so this process is called, as we suggested, stochastic, as we titled the section, stochastic gradient descent. Which we often abbreviate SGD. Okay. It will accomplish two things. Okay. Get at least close to the global minimum. So maybe it doesn't find it exactly, because we're not looking at all the data. So, I mean, in some sense, how could it know what the global minimum is for the entire data set if it's not looking at all of it? Okay. But it'll get close to it. And that's usually, of course, going to be good enough. We're getting close to a minimum for our loss function, even if we don't get quite the whole way there. Okay. The other nice thing about it is it will make the algorithm computationally faster, because we have to run it on as much data. So we sacrifice a bit of optimal performance in exchange for runtime, which is something we often do anyway, and in exchange for this avoiding this kind of these structural issues where we might get caught so this is what I said earlier about getting stuck, right? We might get stuck at a local minimum that's not a global minimum, because the algorithm finds that, and it seems like you're think about it, like you're kind of in a hole, right? And you can't figure out. You're not going to just jump out of the hole. It could be that the global minimum is really far away. So this is the kind of problem. But if you randomly sample data, now you might make some big jump out of the hole, because your data is completely different than the data that landed at that local minimum. Okay. And so that's where the randomness will come into play in terms of how it kind of evaluates the gradient of the loss function on a completely different sort of subsample of the data, and then things look a lot different than where you are. So the stochastic gradient descent algorithm can be tuned with hyperparameters on the gradient descent So in this case, learning rate is certainly the most obvious one that we've talked about. But then there's also stochastic parameters. So how do we subsample, right? Like what percentage, what fraction of the data, and there's some others as well. And on the base learner. So in particular, so tree-specific hyperparameters etc. If you have some other base learner, there might be some other ones, but we're going to kind of focus on the tree case. So in particular, we can tune number of trees, we can tune depth, all sorts of other options. Remember, we're typically when we're doing gradient boosting, we're using shallow decision trees as our base learners. Okay. So all of this can be tuned, as we'll see next week, or well, 2 weeks from now. The tuning process is much more complicated than for random forests, and it's much more kind of step based in the sense of do this first, then do this, then do, and so on. Like we'll have kind of a whole process, kind of a flow chart essentially to go through. So the upshot of doing this, so it's more complicated than what we've talked about before as an algorithm, mathematically and in terms of how we tune it. The upshot is they're very good. So stochastic gradient boosting machines provide very powerful predictive models. Okay. They're flexible, so they can handle lots of different kinds of problems. They're accurate. And they often win or perform well in mathematical machine learning competitions. Such as Kaggle, which you can look up online, go to the website for it, and it provides all sorts of kind of competition data sets and problems. So you've got, it'll say, here's a machine learning problem, here's the data set, do the best you can. Come up with an algorithm that has the highest accuracy or the smallest root mean square error, depending on the kind of problem you have. And so that can be fun. And yeah, so gradient boosting is often one of the better approaches here. Okay, so let's go back in some sense to where we started with chapter 12 and talk about the difference between random forests and gradient boosting machines. So in other words, badgering versus boosting again, but specifically kind of with these two algorithms. Okay, so what's kind of a summary of how random forest works? Okay, so here what are we doing? We're looking at deep decision trees. As the base learner. Okay. The trees are independent of each other in how they're grown, right? So, and as a result, they can be trained in parallel. Oops, that's not how you spell parallel. Okay. They're easy to tune. They're hard to overfit. by which I mean the random forest model itself. Oh, no worries, we're almost done. So if you gotta leave early, that's fine. And I'll just finish talking about random forests and GBMs, and then I'll do a little bit of review for quiz 3. No problem. Yeah, so hard to overfit. They have good, as we've described it, off-the-shelf performance. On the flip side, for gradient boosting machines, we use shallow trees as the base learners. Trees are explicitly dependent. They're grown on each other in sequence. This is because they're trained sequentially. A result of this that we'll talk about next time is that they can overfit more easily. So random forests are hard to overfit. Gradient boosting machines can easily overfit if we're not careful. And essentially, this means that they require careful tuning to perform optimally. So that last point, along with the last point for random forests, will make the following general observation. So a basic rule of thumb that we should always keep in mind is off the shelf, random forest is going to outperform gradient boosting. Or it's going to outperform GBM. But properly tuned, this will flip around. A well-tuned gradient boosting machine is often going to outperform a well-tuned random forest. Okay, and that takes us then to the end of the material for quiz 3. So let's do a little review for that. So quiz 3 is on chapter 11, so random forests, and some of chapter 12. Great, we've up to where we've got to today. Okay, so what do we want to remember for random forests? So the general idea of bagging, since that's the process that we're using for the resampling, and then the split level randomization, which is what we introduced that made this different than just the bagging algorithm we discussed previously. The hyperparameters. Which we discussed how to tune. So remember, what are the hyperparameters for random forests? Number of trees. mtry, which controls the split level randomization. So how many features are we selecting? Tree complexity, so depth and minimum node size and so on, the different ways we can determine how deep to grow the trees. The sampling scheme, if we want to change from the standard bagging approach, bootstrapping. And then the splitting rule, which as we discussed, can often be used to speed up the algorithm. So know the default values, especially for mtry and number of trees. How do we kind of usually pick our defaults there? And then feature interpretation. So as we discussed, we can think about it as total reduction and loss function is usually the way we do this, just like we did with bed. And there was one other, this sort of permutation approach as well. Okay, so for chapter 12, so gradient boosting and gradient descent covered in this chapter so far. All right, what are the base learners? What kind of structure do we want our base learners to have? Remember, high bias, low variance base learners work best here. What is boosting? And what are the boosting fundamentals? What are the main kind of fundamental considerations we keep in mind, such as the choice of base learners, the idea of boosting weak models, sequential training. How do we train the models and how we train them on errors of the previous steps? The tree form. So when we use decision trees as our base learners, we're talking about shallow dependent trees. The idea of gradient descent as a general process, what is it we're talking about? The learning rate. Stochastic gradient descent. So this idea of introducing randomness at the iterations. And then finally, random forests versus gradient boosting, which we just discussed, LRF versus GBM. All right, so that's a review for the quiz. And then just a quick reminder that Thursday, we will not go over any new material. I'll discuss and post a video of just how the project will go. And then we have the reading week break. You have, well, there's quiz 3 on Friday, then the break, and then we'll be back in 2 weeks with new material.